Hi there. In the last video, we saw how a function can also be represented as an ordered pair, where x represents the input and y gives the output or the value of the function at that particular value of x. If you haven't already checked out that video on function notation, a link to that is given somewhere above, so please go and take a look at it. But in this video, we're going to ask this question: does every ordered pair also represent a function? Let's find out. Here's an example from the textbook. And the first question, if you read it, it says, which of the following sets of ordered pairs are functions? Give reasons for your answers. Let's take a look at the first one. Okay, so we've got 4 points, 4 sets of ordered pairs, 1, 1, 2, 2, 3, 3, 4, 4. And let's just illustrate it the way we did it earlier on. Okay, so I'm just going to make a Venn diagram quickly. So I've got the first elements. Remember, these are the x values, 1, 2, 3, 4. They are my domain. So I'm going to write here 1, 2, 3, and 4, right? They are my domain, or I'm representing capital D for that. And the second elements are also 1, 2, 3, 4. And what I mean by second elements, I'm talking about the y values, okay? Y values. So I'm going to put 1, 2, 3, 4 from the range. So that's what we're going to call it as the range. Let's look at the mapping. 1 goes to 1 according to this definition, okay? So that's how they're ordered. 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. So in that sense, when we look at this, is it a function? Well, according to a definition, every element of the domain, 1, 2, 3, 4, every one is accounted for, and every element of the domain is mapped to one element of the range, which means this is a function, and this set of ordered pair is a function. So I'm just going to write f. Let's put a function, okay? Let's look at part C. Next example, okay? This time, let's try and do it without drawing the Venn diagram. Let's try and understand it from this arrangement itself. So these are ordered pairs. Let's understand x is the input, y is the output, okay? 2 goes to 5, -1 goes to 4, -3 goes to 7, 2 goes to -3. Is it a function? Well, we've got every element, okay? -2 goes to 5, -1 goes to 4, -3 goes to 7, 2 goes to -3, each of them going to a unique element or one particular element in the range. This is also a function. And now let's look at part E, all right? In the same way, -7 goes to 0, x value, input, y value, output. The second, -5 goes to 0, -7 goes to 0, -5 also goes to 0, okay? -3 also goes to 0, and -1 also goes to 0, which means different elements, many elements of the domain going to one particular element of the range. Is that allowed? It's a many to one. Is that allowed? It is allowed. It is a function. Many to one is an example of a function. For those of you who have not seen that video on function, the definition of function, the link to that video is somewhere up there. Please go and take a look at it. Many to one is an example of a function. The first two that we saw earlier was 1 to 1, one element of the domain going to one unique element of the range. The example we saw just now, E, is an example of many to one, many different elements, -7 going to 0, -5 going to 0, -3 going to 0, and -1 also going to 0. That is also a function, many to one. Now let's take a look at part D. Let's take a look at part D, okay? Here we've got 3 going to -2. 3 is the input, -2 is the output. But the second entry, 3 also goes to 0. Oh, one input going to different values. 3 is going to -2, 3 is going to 0. But look at the third value. 3 is going to 2. And the fourth value, 3 is going to 4. Input, the same input, 3, is going to the 4 different values, -2, 0, 2, and 4. This is an example of one to many. And according to a definition, this is not a function. Now let's look at example number F, okay? 0 goes to 5, 0 goes to 1. Again, an example of one to many. Look at the other two elements. 2 goes to 1 and 2 goes to -5. Again, an example of what we call a one to many. So this again is not a function. So D and F, because they are of the form one to many, it's not a function. So in the last video, we said a function can be written as an ordered pair. But right now, we have just made a point, a very strong point. An ordered pair is not necessarily a function. The question is, when can we say an ordered pair is a function? An ordered pair by itself is just a relation between the x and the y. Sometimes an equation is also known as a relation because an equation can have an x term and a y term, and there's some kind of relationship between the two of them. Okay, the equation represents that kind of relationship, but not every relationship is a function. So we are interested in finding out, when do we say a relationship is a function? There's a test, and that test is called vertical line test. Vertical line test. Simple, but let's try and understand what it says. Okay, first let's look at the statement. It says an equation is a function. By the way, like I said, an equation is synonymous to relation. Equation is the same as relation. Okay, they are synonyms. Sometimes we use the word equation and sometimes we use the word relation. They're synonyms, right? An equation is a function if any vertical line drawn through its graph will intersect it at only one point. Let's read it again. An equation is a function. We're interested in function. An equation is a function if any vertical line drawn through its graph will intersect it at only one point. Let's try it out, okay? Let's look at some examples here. Here there are some examples of some graphs. And every graph has an equation because, like I said, wherever you have an ordered pair, x, y values, there's a relationship. And so we know a straight line will have, some points on the line, and each point will have its own x coordinate and y coordinate. So there's going to be some kind of relationship between those 2 points. In the same way, there'll be a relationship between points on any of these graphs. And our question is to find out, are these graphs the graphs of a function? In other words, as the question says, use the vertical line test to determine whether these graphs represent a function or is it just an equation. Here we go. So how do we do that? Here's a graph of a straight line, and the vertical line test tells us that any vertical line that cuts the graph in more than one point is not a function. Let's check it out. Okay, so I'm going to take another color. I'm going to draw a vertical line. Oh, this vertical line, any vertical line that cuts this graph of the straight line is going to cut it only in one point. Do you see that? So this is a function. This is a function. According to vertical line test, it passes. Let's look at the other graph. Okay, you may recognize this is the graph of a parabola. So let's use a vertical line test. Any vertical line that passes through the graph cuts it at only one point. So here again, this is a function. Let's look at the third graph. This time it's a graph of a circle. We all know what a circle is. Some of us also know the equation of a circle. But is the circle a function? Let's try it out with the vertical line test. Vertical line, vertical line cutting the graph of the circle in more than 1 point, in 2 points. Before we say this is not a function. You see that? A circle has an equation, the relationship between the x and the y coordinates that lie on the circle. But the circle is not a function because any vertical line cuts the graph of the circle more than 1 point. Not a function. Let's look at the next graph here, okay? We'll study what this graph is later on, but let's just use the vertical line test to figure out whether this graph represents a function or not. Vertical line, and there we go, cuts it at only 1 point. So there, this is a function again. Let's look at this horizontal line. What about a horizontal line? Any horizontal line? Well, a horizontal line is sometimes known as a constant function. And as we saw that every vertical line cuts any constant function in only 1 point. So there again, this is a function. What about this curve out here? A vertical line cuts the graph more than 1 point. Here, again, this is not an example of not a function. Let's read the definition of a vertical line test one more time. What it says is this: an equation is a function if any vertical line drawn through its graph will intersect it at only one point. Let's take a look at some more examples and see whether we've understood this. Okay, here we go. This clearly not a function, not a function. This one, we've already seen this example before. Here we know this is a function. Circle, again, we've seen a circle is not a function, but why? Because of vertical line test. Any vertical line test will cut the graph of a circle in more than one point. This one, what about this one? Draw any vertical line, cuts the graph in only one point. Yes, this is a function. What about this graph? Some of you might recognize this graph. It's a sine graph. Yes. What about a sine graph? Any vertical line drawn through the graph of sine cuts it at only one point. So this is also a function. Yes, this is a function. Now, graph 6 might look a little strange, but we're going to study about these kind of graphs a little later on. But it's just one graph. It's called a piecewise graph. Here it looks fine. But somewhere at the end, look at that, not at the end, somewhere in the middle, you can see those vertical lines out here, these vertical lines cut in more than one point. So this is not a function. So it's not enough that, a few vertical lines cut at one point and, if any vertical line, that's why we have in the definition says any vertical line. You see that? Any vertical line. If it cuts in more than one point, it's not a function. But why does the vertical line test work? Let's find out. I'm going to draw the x and the y axis. I'm going to draw a quadratic graph. Okay. So what I'm going to do is that I'm going to draw 2 points that have got the same y value. Okay. And for different values of x. So let's call this x1 and x2. The coordinates of this point, we'll call it x1, comma k. And the coordinates of this point, we'll call it x2, comma k. Both x1 and x2 are two different x values. They have the same y value, which means this one out here should be k. Let's take a look at this. Two different x values having the same y value. Recall something? Okay, let's put it in our Venn diagram and check it out. You've got x1, x2. I just want to make sure that you can see what I'm writing here. And you've got a value k. Two different x values going to the same y value. This is what we call a many-to-one relationship. And that is a function. Do you see that? That is a function. So any vertical line, if I were to imagine this as any vertical line that goes to the graph, what happens? Because a many-to-one relationship is a function. On the other hand, let's take a look at the other example. If I draw another kind of a graph, something like this, okay? And let's just imagine that there is a x value this time, and there are two different y values, And as we saw, a vertical line that cuts through this graph at x1 will show us that this particular point out here might have a different y value here. This particular point might have a different y value here. As such, the coordinates of this point with the same x value would be x, comma, let's call it k1 this time. And the coordinates of this point would be x, comma, k2. Now let's take a look at this example as a Venn diagram. Okay, so we've got one x value going to two different y values. Can you guys see this? One x value going to two different y values. This is an example of what we call a one-to-many relationship. One-to-many relationship, and this is not a function. And that is why the vertical line test works. Let's take a look at that test one more time, what it says in words, and before we close this video. The vertical line test goes on something like this. An equation is a function if any vertical line drawn through its graph will intersect it at only one point. Otherwise, it is just a relation, just any equation that is not a function. If I have to sum up everything that we discussed today, I'll put it like this, okay? That's the set of all equations And within that, we've got a subset of all functions. What does it mean? It means that every function is an equation, but every equation is not necessarily a function. For an equation to be a function, it must pass the vertical line test. We have just seen how to use the vertical line test to determine whether an equation, which is a set of ordered pairs, also represents a function. If you've been gaining something from these videos of mine, please do consider subscribing to my channel. Thank you, and I'll see you in the next video.